Start. So hello everyone, I'm Ashish Reddy and we are team 2. We are here to present the Wisconsin wireform case study. So this is my team. So this is Hang, this is Vladimir and this is Hao. So I'll be first taking you through the introduction part, then followed by Vladimir. Thank you. So let's start off with the basics. So this is the basic outline of the business. So the business started in a garage outfit in 1999. It's a component and supplier manufacturer for a wide range of industries. So major customer industries by sale are agriculture, automotive and recreational vehicles. So they are also growing in a new construction business, which is a 2.3 million business currently. So the annual sales for Wisconsin Wireforms is 22 million and they have a workforce of 200 employees. So they are like 60% of the company's sales are from make to stock and 40% are from make to order. So these are the current state problems that the business is facing. So the first one, as we can see, there's high percentage of non-touch time, so the white spaces that we have studied. And the second one is the lead time spiral is occurring in the organization. So with same amount of demand, the lead time is increasing, so they are facing the lead time spiral. So and the costs are steadily increasing for the same business volume. Only 70% of their delivery performance is on time, so they're missing about 30% of the delivery. So high raw material, work in progress and finished good inventories are other problems. So this leads to high sales loss due to high lead time, and there are also low profit margin and high revenue due to high cost. So at the outset, so these are the potential savings that we can see from reading the case study. So the first one is they're spending about 1 million a year for expediting their processes. So and scrap and rework are about 5% of their annual sales. So this accounts for about 1.1 million a year. So it's also mentioned that they work almost every Saturday. So taking that into account for the overtime cost, it's about 1.2 million. Also, due to less warehouse storage, they are planning to expand their warehouse and spend about 10 million. So the potential quantifiable annual savings, if we add the first 3 points, is about $3.35 million. So a significant cost which are missing is the penalty cost that is due to the late delivery. So as I mentioned, they hit their target only 70% of the times. So they're missing their delivery about 30% of the times. So this cost is not considered. So also, as we have learnt in class, the lead time reduction also has other hidden benefits like quality improvement and overall cost reduction. So this is the basic motivation for us to implement the QRM cell at Wisconsin Wireforms. The first point is reduced inventory cost, reduce expedite expenses, which they are spending about 1 million a year currently, reduce scrap and obsolescence costs, improve on-time delivery performance, improve quality and reduce the cost of goods sold, increase revenue margin, and increase spare capacities and potential sales if there are any demand spikes. Okay, so the first thing we do is for the QRM process is start by identifying our focus target market segment. So we have 3 parameters here: revenue, volume, and lead time. So based on all these parameters, we select our FTMS. So we want to avoid. So the main point is we want to avoid recognizing the whole company at once. So this will create a mess. So we want to start small and make a large impact. So the focus target market segment we selected was construction. So this was based on the market opportunity. This is a quote from the case study by the Vice President of Engineering, which mentions that the construction business we are trying to grow is creating issues. So they need changes. So we selected construction as our FTMS. So now this process of selecting FTMS and our part families will be taken over by Vladimir.
All right. Thank you. So this was one of the preliminary decision justifications or data explanations for how we chose our part families. What you can see is on the y-axis we have machine participation across all part families. So for a given part, how many machines participate for that part, except in this chart along the x-axis we see the different machines that participate in each or in the different parts and what their popularity or participation is across all the parts that this company produces. What we find is a confirmed Pareto distribution where the S machine or the straightener contributes to, or it participates in 86% of the different part families that we looked at, and then we see a pretty steep drop-off. So in selecting part families, we want to try to cater towards that larger distribution to have more of an impact without having excessive specificity or over-specialization. However, that isn't the only criteria that we used in making our decision. Highlighted in yellow are the machines that we actually chose for the part families we selected for our cell, and you'll notice we actually skipped over FT for other criteria that I'll go into next. So what we did was we took the data supplied by the customer, or the client rather, and we divvied up all the different part families and all the machines that are involved in that process. After that, we weighted each of the values. So if you see a value like P18 and S, that means that S participates in part family 18. Instead of just a 1, we actually put the part volume for each of those intersecting values, and then we just added the sums of all these rows to get a value for how popular, how much participation the machine has. And then we ranked all the machines in order of peak participation going down right here. From this information, we found that if we wanted to have roughly 5 machines in a cell, we could support several part families. However, this one was a little bit different. So this is part A. We found a 41.8 cumulative demand, so that's quite good. 5 machines, that's great. And we had a total of 9 market segments. Part 13 adds an additional 2 market segments, so we were considering that as the next option. Option B, so this is a slightly different approach. We added an additional machine here, FT, and this allowed us to extend our selection up to, let's see, P5 and P13. So we add an extra machine, but we also added 2 more market segments. With this in mind, we had to create sort of a tiebreaker between these 2 choices. I think this tiebreaker would involve a bit more communication with the client or the company. Essentially what we're aiming for is we want to cross-train our workers to take full advantage of quality improvements. What we have to do though is we have to justify, or we want maximum participation or part participation, part coverage for impact in the cell. So we have to justify this increase of 9.4% part coverage within option B, but that comes at a price of an additional 2 market segments, right? So we want our workers to be versatile and cross-trained, but there's also a huge benefit to being focused within a particular market segment so that you can really get better and find quality improvements. So with that in mind, we figured that part 5 and part family 13 were not justified in the initial stages of this cell, but they could be added later to get that 9.4% part coverage. All right, and then in summary, for identifying our part families, here are the part families that we selected, their annual demand. So we're covering a total of 49.79% of all the part family, or all the parts that we'll be producing. This allows us to get really the core of your business covered within the cell. And then specifically with regards to construction, 58% of all the construction parts can be made within this cell. We, again, just summarizing the selection criteria, we wanted part families that would make an impact on the business but weren't unnecessarily complicated and were just reliable and high quality to keep the business running smooth. We wanted a similar routing process, and we wanted to try to minimize the number of machines within the cell, so we stuck to roughly 5. Here are the machines that we listed, and next we'll talk about, I believe, our resource routing. All right.
Next, we're talking about the resource capacity analysis. This is basically to determine how many machines and laborers we need to use in our cell. And first, we made some assumptions. And for the working hours, we decided to work 5 days a week, and we don't want to work overtime, so we only have 8 hours per day for the work. So therefore there is total 2,080 hours per year. And for the equipments, we assume the mean time to repair and mean time to failure follow the Bernoulli distribution, and 10% of the time will be for the repair, and 90% of the time will be for the failure. And then for the average run rate and average setup time, it's just calculated based on the table we are given. And for the labor, we decided we want the number of labor to be equal to the number of machines. And we also have 10% of the time for labor available. And here is just like a summary of our calculated results, and we show we can, like, for the machines, it's like the maximum number of machines we can use, and we then calculate the working time and setup time and repair time and available time, and these are just some formulas we use. And then we like implement our model into the MPX, and so like this is our base case, and basically we just input all the like data we get into the model and do the first iteration of the calculation. And here you can see this is the static state, and the lead time is just from the table we are given. And this is the result of the calculation, and you can see for the lead time, and the lead time for part family 1 decreased by like 15%, and for part family 2 it decreased by 13%, and for part family 3 it decreased 25%, and the lead time for part family 6 decreased the most, is roughly 40%. And here is the like working process inventory, and you can see like we have the most working process inventory for part family 8. And here is the setting, and in our base case, we just choose the lot size to be 13,000, and this is just again from the table we are given, and we just calculate from here. And again, the labor and the equipment ratio would be 1. And here's the analysis of the utilization of our baseline of our base case. And you can see there are some like major observations we can get. And the most important one, the operation can be done using like 9 machines, like 1 for S and 2 for CNC, 1 for P and 1 for X and 1 for C. And you can see from the figure, and for both the labor utilization and the equipment utilization, the setup utilization for X and S, like the blue region, are both pretty high. So we want to reduce that in the following steps. And we can see our labor utilization is low enough now to like keep the operation running. And in this case, our like MCT reduction is not very significant, so we still need to do some more improvement. And Hao will tell about how we continue improve the process.
Okay, thank you. Okay, according to the observations we got from the baseline analysis, we could say the setup time here is very large, and also the waiting for labor time is accounts for a large part. So we could have several improvement policies. Our dynamic analysis consists of 2 parts. The first part is we could make some improvement policies. First, we propose some setup reduction policy. We times factor 0.5 to all the machine to the machine S and X. Second is a downtime reduction. We time the factor 0.5 to all the machines to preventive maintenance. And third is cycle time improvement. We times a factor, actually 90% to all the operations. And finally, as we are saying from before, that our machine has a large time for waiting for label. So we just use cross-training labels in the cell. This is our first step. Second step is based on the observations we got from the dynamic analysis. We got new observations, and then we're going to continuously improve our performance. We're going to propose some optimal lot size, so we're going to explain it later. First, let's just look at our step one. Oops. This is for the improvement policy. After we change the parameters, we can see that for the MCT and the weight value, there for part family 1, 2, 3, 6, its value decreases a lot. For the MCT on average, it obtains a decreasement of about 25%, and for the weight value, it decreases about 35%. So the same conclusion can be drawn from the equipment utilization. We can see that after changing the parameters for the setup time and the downtime, the setup time actually decreases a lot. And of course, for the waiting for labor, you cannot say there is just only tiny part for the waiting for labor. Okay, so, but we still have our problems. When you look at MCT value, MCT figure, you can see that there is a large part for the waiting for rest of lot. And when you are looking at that weight value, you can see the weight value for part family 1 and 3 are still very high. So think about what does it mean by waiting for rest of lot? Because the MCT only focus on one single part. That means this one, only one single part is waiting for other part in the lot to be processed in the machine. So that means actually our lot size is not appropriate. We want to decrease our lot size. That we just propose our dynamic analysis step 2. We change our lot size. Then we conduct a dynamic analysis. We change the lot size from 30,000 to 3,000, and we will see the MCT value actually decreases when the lot size value decreases, and we got a near optimal value around when lot size equal to 3,000. The same conclusion can easily drawn from the equipment utilization. This is very obvious. While the lot size is decreasing, our equipment utilization increases. And we can only look at machine S, and you can see the utilization approaches 95%. Actually, that's nearly the full utilization of that machine. So we got our final conclusion that the near optimal value of lot size is around 3,000 part. And we just change parameters of optimal, and our final observation just support our estimation. We got an average 75 reduction of the MCT for all the part families, and actually 74 reduction for the weight value. And you can see from this figure, this part waiting for rest of lot decreases a lot. That's support our estimation, and the weight value also decreases a lot. Let's have a summary of what we have done for the experiment. Actually, we have 4 experiments here. The first one is static, which we just grab data from the handout. And for the baseline, we calculate setup time and processing time from the table, and we make some assumptions, and we got the baseline. And for the improved one, we changed the setup time to be like 50% and changed the setup time to be 90% of the original one. We got our improved one. And finally, for the optimal one, we changed our lot size. We got the optimal case that we have to use 9 machines and 9 labors. We got our optimal case. So the final conclusion would be our average reduction of MCT would be 81% reduction. That's really a big reduction. Okay, then Vladimir will give you our proposed cell design.
Thank you, Hong. All right, so now that we have a full-fledged MPX model with considerations with regards to labor, resource utilization, routing, etc., we're proposing a cell design. So we start with phase 1, and then we'll go to phase 2, right? So I'll go through phase 1 first. The best cells is where the workers are cross-trained. That way you get all the benefits listed here. You have improvements in quality because the workers understand more of what's happening along the chain. You have increased efficiency with fewer defects. You have increase in production. You have fewer errors. You have decreased fragility because, say, one CNC operator gets sick, you'll have another one that's able to fill in the void. And then overall, you're creating conditions that'll decrease your MCT. So all of this won't happen overnight. So what we recommend to this company is to start implementing these labor groups within the cell. So start with 3 people specializing in the straightener and the CNC machine, and then have a total of 6 people on C, X, and P60. So chamfering, extrusion, and press. The reason that these, well, all of these recommendations are informed by the MPX model, but just as a refresher, the most important machines, the ones that affect all the parts, are outlined in red and bold. So that's a straightener and the press, and that's where we want to put all the emphasis. And you'll notice that we have 1 straightener and 3 workers. We have 4 presses, and we have 6 workers here. So in the initial implementation of the cell, focusing on those 2 machines is what's going to keep the cell running, right? CNC and chamfering are outlined in the light blue. That's to signify that the workload for that particular machine isn't that intense. They're fairly interchangeable, and recommendations can be refined. The routing within the cell is outlined by the arrows. The different arrows signify the different part families. So for example, the high volume family part 1 starts with the straightener, it goes to CNC, and then progresses to P60. So that is your most critical part in the cell, the highest volume. And then in descending importance, you have P2, then P3, then P6. And then lastly, physically speaking, you want to orientate your cell sort of in a U shape, so you have parts coming in, and then rotating through, and then leaving. And then let's go to phase 2. So here, this would be sort of the final stage of a properly running cell, where all your workers are fully cross-trained, and that gives you the benefit of being of decreased fragility, which is what I write here. So if some of your workers get sick, or say conditions change and you have to be a bit flexible, your workers are highly trained so that they can adapt. You can decrease your product to market time, they'll manufacture quicker, higher quality, lower waste, and you get all the benefits of cellular manufacturing. So with that, I'll pass on to, I believe, Ashish. Yes.
Thank you, Vladimir. So I'll be going through the financial justification for the cell. So first, so these are the assumptions for the financial justification that we made. So for the work center and equipments, so forming a QRM cell requires rearranging machines, so they are co-located. So equipment rearrangement involves the cost of moving machines as well as the cost of loss of production during the time the machines are moved. So we considered a 1 week time for moving the machines and creating a functional cell. So for the labors, for all operations, the labor cost is considered at $20 per hour, and for cross-trained labor and overtime wages, we considered 1.5 times of the value, which is $30 per hour. So we'll be going through the costs that we incur during the formation of the QRM cell. So these costs are divided into 2, which is one-time and recurring. So one-time costs are costs like plant preparation, equipment moving, revised product routing, cross-training of labor. So plant preparation, so as I told you, we assumed 1 week time to move the equipments and create a functional QRM cell. So there is loss of production during the time. So we considering that we came up with a figure of 400,000. So and for moving the equipments, we have a value of 20,000 per machine, which comes up to 180,000. So revised product routing for the 4 part families is 20,000. So cross-training of labors, so we have 9 labors, and so for each one we consider a one-time amount of $10,000 per labor, which comes up to 90,000. So and now we come to recurring costs. So high wages due to cross-training. So as we told you in the previous slide, we considered $30 per hour for cross-trained labor compared to $20 for the normal labor. So we have 9 labors, and so an additional $10, and they work 8 hours a day into 260 days, which comes up to 188,000 per year. and QRM consulting per year to implement changes or do continuous improvement is $30,000 per year. So if we add up all the costs, so the total cost for the first year is about $898,000 for the first year, and in subsequent years it is $218,000. So next we look at the benefits that we get from the QRM cell. So as I mentioned previously that the company spends about 1 million every year in expediting. So we eliminate, so by forming a QRM cell, we eliminate expediting all parts in the cell. So we covered about 41.2% of parts in the cell. So we considered like 41.2% of 1 million, which is 412,000. So reduced scrap rate. So the scrap rate was about 5% of the annual sales. Now within the QRM cell, we consider reduction of 3%. So 5% from 2%, which gives an annual savings of 181.2 thousand per year. A reduced overtime cost. So the 9 laborers within the cell don't work every Saturday as mentioned previously. So which amounts to a saving of 112,000 per year, and reduced inventory holding cost. So because of the MCT reduction and there's a WIP reduction of about 74%. So if you calculate based on the annual sales, making a few assumptions, we get a dollar amount of 235.5 thousand. So this total benefits per year is about 941,000 per year. So in summary, the total benefits is 941 minus the 898K for the first year. So the total benefits is 43,000 for the first year, and the payback period is only 1 year. So the other benefits which are not quantifiable are the value of on-time delivery and very low lead times. So as Hang mentioned, we reduced the MCT by about 81%, which gives us very low lead times and will give us an advantage in the business. The other benefits we weren't able to quantify is the penalty cost for late delivery. And as we have learned that the QRM implementation also improves the quality and cost improvements. So these are our final recommendations. So implementation of the QRM cell. The FTMS we chose was construction. The part families selected were 1, 2, 3 and 6. So we have a total of 9 machines in the cell. There are totally 5 types of machines. So we have 1 straightener, 2 CNCs, 4 presses, 1 X and 1 C. And the labor, we have 1 labor for each machine. So we have a total of 9 labors, and CNC and the S machine straightener share 3 cross-train labors, and the other 3 machines share 6 labors. So the lot size, the near optimal lot size was 3,000 for all part families, and the organization structure we propose, which will promote continuous improvement and individual ownership within cell. Thank you.